Hello, let's look at section 11.3 today, and 11.3 is all about the area of polar curves. So one thing that we'll want to make sure is that we can recognize equation formats of various polar equations. They'll give us some idea of what to expect and easier to graph out if we have an idea of the shape of them. So you've got your limmations, and we've got that inner loop, the cardioid, the dimpled, the convex, all dependent on the ratio of A to B. And then the rose curves, we know if we get an n being odd, then we're going to have that number of petals. If the n value in front of your theta is even, you're going to have twice as many petals. Okay, so keep those in mind. Another thing is just kind of looking at how long it takes to complete the curve, like 0 to pi, 0 to 2 pi, things like that can help you understand the shape that you're trying to calculate the area of and what your bounds will be for your integral, because that's probably the hardest part about polar area. We are very familiar with rectangular curves and doing the rectangular area under the curves, the Riemann sum idea, the trapezoidal method, and integration. When we switch over to polar area, it really becomes the area of a sector. So you recall from geometry that we call a sector kind of like a piece of pie. And that shape, or that area of that shape, can be calculated. So let's walk through what that calculation looks like. I could set up that I know the area of a full circle is pi r squared. And if I want a portion of the circle, then I'll just talk about what portion I have out of the complete rotation 2 pi. So I'm going to call it theta over 2 pi. What we notice is that pi does cancel in that case, giving us 1. And so I end up with a formula that looks like 1 over 2 r squared times my theta. But in order to be really accurate with our, let's say we don't have just a nice little circle, so we want to make these into small little sectors. So think of this area. Well, my amount of rotation here is going to be very, very small. In fact, we'll call it infinitesimally small, d theta. So this theta that we're seeing here will really become d theta, and that is where we're getting our formula. And probably most of the time we will bring the 1/2 out front. Our bounds will be from a theta angle starting at alpha, finishing at beta. So that's why you're seeing alpha to beta. R squared is the length of that radius, that directed length, and that's going to be given to us by the polar equation. So we really can substitute for R the polar equation F. And there's the formula, okay? So we'll roll on with that. So the first one says calculate the area of this cardioid, and it had R equals 2 times 1 plus 2 cosine theta. We also could see this as 2 plus 2 cosine theta, right? And know that that's a cardioid because A and B are equal as they are here. And there's a 1 in front of there. So let's sweep this around. What I want to do is think about how did that cardioid graph out? Where was the beginning point for it? So I'm just going to go ahead and say, okay, when I started at 0, cosine of 0 is 1, 1 plus 1 is 2, 2 times 2 is 4, and I would be out here at 4, 0. So that is my beginning point, and the directed length was 4 on the angle of 0. Next, I'm going to step up. Let's see, where's cosine kind of nice? Let's do cosine of pi over 3 because that's kind of a nice value. Pi over 3. Well, that turns out to be 1/2 plus 1 times 2, so I'd have 2 times 3/2 or 3. So at pi over 3, I would be up here at 3. At pi over 2, we know this is going to zero out, so I'm going to be at a height of 2. And you can imagine that all of these are getting plotted, right? And finally, when I'm at 2 plus cosine of pi, well, cosine of pi is -1. That makes a 0. This comes into the origin. What we have just done now is we have traced or span the area of the upper curve. If I continue on, I will come all the way around to 2 pi. So what I could do is go from, let's calculate the area. The area is equal to 1/2. The alpha that I'm going to start at is 0. And I could stop at pi if I wanted to. Then I would just have to double my area because the top half and the bottom half have symmetry in the same area. Instead, I think what I'm going to do is go ahead and just work my whole way around and let this sweeping motion completely track the entire cardioid. So I'm going to go 0 to 2 pi of, what was our curve? 2 times 1 plus cosine theta d theta. If I were to do this by hand, I'd probably bring the 2 out front and cancel with the 1/2, making or multiply it and getting 1. And that would make this a little bit easier to calculate by hand, getting us an area. I'm going to just go ahead and find the answer so we don't have to do it by hand, of 6 pi. I'm going to trust that you can do that integration. Okay, I want to see what this, it is loading, and I am going to bring this over onto the screen. So there is an area. It is our formula. You can see how this does just fill. The more I get, the more accurate it is. So what we're doing is increasing the number of ends, which is giving many, many more sectors to our area. But I like this because it does show you this sweeping motion. Now, let's continue around and say we want the whole upper half. So I'll come back to the origin and let's increase our n. You can see how it's not moving much once we got out to, n even back here. We're at 9.5 and we stay pretty much 9.5 for that upper half. So if I double this, I'm going to be around 18. Well, our answer was 6 pi. So 6 times 3.14, we're pretty close to, with that estimation on that little applet that we just went through. Next, it says, sketch the curve, calculate and shade the area of one petal. And I got to move. I can't move it. It is 4 sine, isn't it? Oh, it's 4 sine 2 theta, which will give us, right there it was, 4 sine 2 theta. Since theta has a 2 in front of it, it is an even value. And I know that means to double the amount of petals. So I can expect 4 petals on this one. Since it's sine, they are going to track out symmetric over pi over 4. So let's see this happen. And I think the best way, because you don't have a lot of experience yet graphing, let's just take some values. So let's set up our theta, get our r. If we throw in 0, we know the sign of 0 is 0. So this one definitely starts at the origin. Let's go on to pi over 4. We throw in pi over 4, that makes a pi over 2, that makes a 1, that is 4. Oops, this was 0. And if I go pi over 2, I am back at sine of pi, which is 0. So somehow this starts at 0, comes out to 4 when I'm at pi over 4, and then back to 0 at pi over 2. You may want to see a few more values in between. If I did pi over 6, that would be behaving like 2 times pi over 6, like a pi over 3. Sine of pi over 3 is root 3 over 2. So I'd have 4 times root 3 over 2, which gives me 2 root 3. That's going to be, I'm just going to say approximately 3.5-ish. So at pi over 6, we will be out at 3.5. And much could be done the same at pi over 3. Now you can get a feel for that first petal. All right. So these 3 petals are going to fall in line. Oops, 3.5. Up a little higher. We're going to have a petal situated in there. We're going to have a petal, just go ahead and mark all of yours in 3.5, 4, 3.5. 3.5, 4, 3.5. Okay, so we've got our rose curve done in. They just want us to find the area. Let's go ahead and shade one petal in. I think the easiest one's going to be to grab the quadrant 1 petal and talk about the area a bit. So now I just need to come up with what are my bounds. I know the formula has a 1/2 in it. Well, I started with 0 and that plotted at the origin. And then I went out to pi over 4, got to my longest portion, and then at pi over 2, it came back in, and that completed the first petal, pi over 2. The formula was 4 sine 2 theta, which gets squared, and then d theta. You know what? I just realized, did we not square? I did not square on this, you guys. We need that squaring. So this 2 will get squared, making that 4. And so I should have a 2 out front here. And then you'll get the 6 pi. But you caught me on that. Glad I was able to go back and backtrack that. All right. We could calculate this out, of course. I would probably square and get 16. 16 times 2 is 8. 0 to pi over 2 of sine squared 2 theta d theta. Probably would have to use my formulas. It's been a while since we've done those. If we were to do these by hand, the squaring one. So I would go 1/2 minus 1. Let me write it the way you'll recognize it. 1/2, 1 minus cosine, double the angle of 4 theta d theta. And then I would be able to integrate that. So I'd bring that half out front again and get a 4. Okay, the answer on this, I'm trying to find it. It did come out to be 2 pi. We went from 0 to pi over 2. So some of those old trig identities will be helpful if we have to do it by hand. For your homework, you can go ahead and use your calculator today. Area between these curves. So if I have an outer curve and some sort of inner curve, how do I come up with that blue region? Well, one thing I could do is I could calculate the area all the way out to the outside one. That would be the big R squared. And then I could go after the area of this inner one, just going out to little r. That would be this calculation. And if I take the yellow minus the red, it'll leave me the blue. So this is one way you can calculate it. If you'd rather throw it together instead of having 2 integrals, you can put a shit together and say big R squared minus little r squared, which is very much like Washer method to us when we were doing rectangular volume of revolution. So it might be somewhat easy to remember. This one says, what is the area of the region that lies inside r equals 3 sine theta, and outside the region r equals 1 sine theta. So what kind of shapes are those? Well, hopefully you can recognize that this is a circle. Its symmetry is the y-axis, and its diameter is a 3. So we'll get that one laid out. I need to move that so I can work with that a little bit. Then the other one, I see that we have equal A and B, so this one must be a cardioid. And you'll just get better and better at these the more that you force yourself to recognize them. Should have an I in there. So 3 sine theta. That will be, I put in 0, I get out 0. If I put in pi over 6, I have 1/2. 3 times 1/2 will be 3/2. Likewise, it'll be over here. And if we put in pi over 2, will be up as high as 3 right there. So we get a circle formed symmetric over the y-axis, or the pi over 2 line. Next, let's talk about the cardioid. It is positive in between A and B, so I know it's on the upper half plane. I know its symmetry is over the y-axis. I know that its longest segment will occur when I'm at pi over 2, which will give us 2. So that'll be right there. When we're at 0, we get 0. When we're at pi over 2, or pi over 3, that's 1/2. I'm going to get 1 and 1/2. Ooh, looks like they have that in common, doesn't it? Which would mean they have it in common over there. This is going to map out, trying to draw it like this. So I'm going to start and come in. There we go. It'll be something like that. Oh, you know what? We should be at 0. We actually start at 1, don't we? And these are going through or something like that. All right, and they want the region outside of the cardioid, but inside the circle. That will lead us to that region that you're seeing over here, this portion right here. So we're going to use big R squared minus little r squared to do that. Let's just get rid of this. We can. I have some writing room. All right. So my area is going to be 1/2 big R squared minus little r squared d theta from alpha to beta. Therefore, we're going to get 1/2. We need to find that intersection point, and we actually did find it when we were plotting. But if you were uncertain, we can just do it like we would do for rectangular, the intersection. Set the equations equal to each other and just solve them. So I'm going to minus a sine theta. And obviously that's going to give us 2 sine theta. I'm going to divide by 2, so I get 1/2 equals sine theta. And then you can think to yourself, where is sine equal to 1/2? Or you can take it to that next level and say, okay, theta is going to be equal to sine inverse of 1/2. And sine inverse of 1/2 occurs when we are on pi over 6, 5 pi over 6. That's where they're positive. And indeed, that is where we noticed that intersection. Theta was equal to pi over 6 there, and theta was equal to 5 pi over 6. Of course, I could use symmetry too and just go with half and double, so I could stop at pi over 2 if I wanted. I'm going to do just the full sweep from pi over 6 to 5 pi over 6. Big R is my outermost segment, right? Stretching all the way out, there's big R, and that is the circle formula. So 3 sine theta squared minus the little r being just to that point, and that formula was the cardioid. 1 plus sine theta quantity squared, and then we want to multiply that segment by d theta. And that will take care of the area calculation for it. The area turns out to be, oh, this is crazy, it turns out to be pi. So there's a quick little go over on polar area. They really do start getting fun and get a little geometric spatial going when you have the intersection of two polars. So your homework for today is this worksheet. There may be some repeats, maybe not, of what we practiced on notes, but if so, I guess lucky you. The backside, just go to 7 for today. For this year, I'm going to cancel off number 8 since we've already taken the AP test. Thank you.